Good morning, everybody. It is Tuesday, December 19th. Oh my god, yesterday the weather was absolutely atrocious. Holy moly. I had a flat tire. Oh god, it was just awful. Power outages made it hard to edit videos. But here we are, we're in the final stretch. It's episode 19 of the AP Calculus Free Response Question Advent Calendar. There is chocolate number 19, which I will promptly get into. Will I put today's free response question on screen now so you can give it a read? We are really in the final stretch here. Today's problem is one of those applications of derivative problems with some water in a tank. There's a couple functions going on. We got a few like select values of a function. We'll use the intermediate value theorem. We're also going to get to do a left Riemann sum, so that's fun. I feel like that can get complicated in people's perceptions, Riemann sums, because sometimes it feels like there are a lot of steps. It's really simple though once you understand what's going on. You got to understand the concept, right? Not just the steps. If you're memorizing steps, it makes it way harder. Especially after getting gifts from my students. I have so many sweets. This is just ridiculous. So many chocolates. God, that's a great chocolate. Okay. Let's do the calculus. This is free response question 1 from the 2016 AP Calc AB exam. This is part of the graphing calculator section. We will use a calculator a couple times throughout this video. Water is pumped into a tank at a rate modeled by W of t equals 2000 e to the negative t squared divided by 20 liters per hour for t between 0 and 8, and t is measured in hours. Water is removed from the tank at a rate modeled by R of t liters per hour, where R is differentiable and decreasing from t equals 0 to t equals 8. Selected values of the function R of t are shown in this table, and at time t equals 0, there are 50,000 liters of water in the tank. All right. Part A is to estimate R prime of 2 and to show the work that leads to our answer and to indicate units of measure. Remember that R is the rate in liters per hour at which water is being removed from the tank. So in estimating R prime of 2, we're estimating how fast that removal rate is changing at t equals 2. Now, all we have are a few values of R of t. So in order to estimate R prime of 2, we're going to have to estimate the rate of change near t equals 2. The closest we can really get to that is looking at how R of t changes from t equals 1 to t equals 3. If we find the average rate of change from t equals 1 to t equals 3, that will give us the best approximation we could get for R prime of 2. Let's go ahead and put part A down here. We are trying to estimate R prime of 2. And we know that R prime of 2 is about, we need to do some division here, it's about the change in R from t equals 1 to t equals 3. So R of 3 minus R of 1, that's going to tell us how much R changed on that interval, and then divide by the width or length of the interval, so 3 minus 1. This tells us the average rate of change on the interval. The interval contains 2, so it's a rough approximation of the rate of change at t equals 2. R of 3 we know is 950, and R of 1 is 1190, so our numerator is 950 minus 1190. The denominator, of course, 3 minus 1, the interval length, is just 2. And this is negative 120. Don't forget, we also need units of measure. R, the original function R, was in liters per hour, so negative 120 liters per hour, but this is an estimation of the rate of change of R, so this is actually liters per hour. You could also write this as liters per hour squared. This is how fast the rate of change, that rate of removal, how fast that rate of removal is changing. All right, moving on to part B. Use a left Riemann sum with the 4 subintervals indicated by the table, so 0 to 1, 1 to 3, 3 to 6, 6 to 8, those 4 subintervals, Use this to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or an underestimate of the total amount of water removed? And give a reason for your answer. Okay, so if we look at the table up here, again, this is giving us values of R of t, a few values for how fast water is being removed at different times. If we were to integrate this function, R of t, from 0 to 8, that would accumulate all of those removal rates, and thus tell us how much water is removed in total. Now, we don't know what R of t is as a function exactly, so we can't actually do that, but we can approximate that integral using a left-Riemann sum. And again, what we're approximating is the integral from t equals 0 to t equals 8 of our function R of t. So this is the integral of R of t dt from 0 to 8, and we're going to approximate it using a left-Riemann sum. A left-Riemann sum means that we're adding up rectangles whose heights are determined by the left endpoints of our intervals. So if this was an x-axis, for example, our first rectangle, starting at t equals 0, would have a height determined by this left endpoint. So it would be a height of 1340. So it would go up here to 1340, and it'd have a width of 1, because we're going from 0 to 1. So let's maybe draw it a little bit less wide. It has a width of 1, and it has a height determined by the left endpoint, so 1340. The next rectangle in our Riemann sum would be going from t equals 1 to t equals 3, and its height is determined by the left endpoint, 1190. The height of this rectangle is 1190, but the width is 2, because this interval width from 1 to 3 is 2. So that rectangle might look something like this. It's a little bit lower, because its height is 1190, but it's twice as wide. So I'll put a 2 down there, and an 1190 there. The third rectangle, I'll write in orange, is over this interval from t equals 3 to t equals 6. Its height is determined by the left endpoint, because we're doing a left Riemann sum, so it goes down some, starting there maybe. And the width of this rectangle is 3, because it goes from 3 to 6. So let me sketch this. It starts at about 950, its width is about 3, so maybe it looks something like that. Again, the height is determined by the left endpoint. And there's the last rectangle with a width of 2, from t equals 6 to t equals 8, its height determined by the left endpoint of 740. So to find the approximation of the integral, we just have to add up the areas of all of these rectangles. The area of a rectangle is base times height. So that would be 1 times 1340, plus 2 times 1190, plus 3 times 950, and so on. Those are the areas of the rectangles, and these add up to 8,050 liters. So we would approximate that about 8,050 liters of water were removed from the tank from t equals 0 to t equals 8. But remember, we are not done, because part B also asks us to determine if this approximation is an overestimate or an underestimate of the actual total amount of water removed. And we're able to determine the answer to this question based on knowing that R of t is decreasing. So R of t, if we were to sketch it in, say, this reddish color on this same graph where we sketched the rectangles, because R of t is decreasing, it might look something like this. And so you can see that all of the rectangles are overestimates because they lie above the curve. Because it's decreasing, we know that this left Riemann sum is an over approximation. All right, moving on to part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So we need to consider how much water was in the tank to begin with, 50,000 liters, add in the amount that is pumped. Remember that W of t, this function's telling us how much water is pumped into the tank over this interval of time. And then we need to subtract the amount which is removed. And we know a rough approximation for that. That came from part B, about 8,050 liters are removed. So our answer for part C is going to be 50,000, the amount that was there to begin with, plus the accumulation of all the water that's pumped in from t equals 0 to t equals 8, minus the approximate amount that is removed. Again, this is just an approximation of the total amount of water at t equals 8. Now, to integrate w of t, this function here, from t equals 0 to t equals 8, we will crack open the calculator. So I'll press the math button to access my functions, press 9 for the integration function. We are integrating from 0 to 8. The function that we are integrating is w of t, which is 2000 times e to the negative. We'll use x as our variable for convenience, so negative x squared divided by 20. And this integral is taken with respect to x, and this is about 7,836.195. That's how much water is pumped into the tank during this time. So we have 50,000 plus this integral was about 7,836.195 minus that water that's removed, 8,050. This turns out to be about 49,786 liters of water in the tank at time t equals 8. All right, moving on to part D. For t between 0 and 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So to answer this question, we have to consider the amount of water being pumped into the tank, w of t, minus the amount of water that is being removed, which is r of t. That difference should be 0 at some point between t equals 0 and t equals 8 in order for the functions to be equal. In order for the rate at which water is being pumped in and removed to be the same, their difference needs to be 0. Now, the difference of those functions is continuous and differentiable because we know that both w is differentiable. We can look at it. We know that's a differentiable function. And r of t is differentiable because we're told as much. So we can apply the intermediate value theorem. And here is all of that logic written out. W of 0 minus r of 0, the initial difference in the pumping and removing function, is 2000 minus 1340, which is positive. We know this because if we just plug 0 into w of t, we're going to get 2000 times 1. So that's 2000. And we're also given that r of 0 is 1340. So that's where those numbers come from. We see the initial value of this difference is positive. The ending value, though, w of 8 minus r of 8, is negative. We know that because we can just plug 8 into w of t. Just do that on the calculator. You get about 81.5. And then subtract 700, that was given to us. R of 8 is given as 700. Clearly, this is negative. So this difference between W and R, the pumping in rate and the removal rate, was initially negative. But at the end, it was initially positive, but at the end, it was negative. Because this difference is continuous on the interval, we know that the intermediate value theorem guarantees at least one time t between 0 and 8 for which the difference of the functions had to equal 0. It was positive, then it was negative, so it must have crossed 0 at some point, and at that point in time, w of t, the pumping in rate, was the same as r of t, the removal rate. So at this time t, the rate at which water is pumped into the tank equals the rate at which water is removed from the tank. That's how you solve this part using the intermediate value theorem. And that completes our solution to free response question 1 from the 2016 AP Calc AB exam. Let me know in the comments if you have any questions, and I'll see you tomorrow for another episode of the AP Calculus free response question advent calendar. Make sure to check out the other episodes if you missed them. There's a link in the description to the playlist. I'll see you tomorrow.